Okay, in this lab, we're going to look at oxygen, producing oxygen. Okay, we want to get some oxygen and measure some properties. Okay, so here we go, oxygen. Okay, now oxygen is usually found as a molecule, right? A diatomic molecule, O2. Okay, now the air that we breathe is about 78% N2, diatomic molecule, for nitrogen, and about 21% oxygen, and about 1% other stuff. Okay, so it's mostly nitrogen. Quito. What we want to do, well, we'll talk about the experiment in a second. The first thing we do in this lab is we look at the decomposition of oxygen containing elements. Okay, decomposition of oxygen containing elements. Okay. First thing we look at is what's called sodium nitrate. Sodium nitrate. Okay, that's Na is sodium, NO3 is nitrate. Okay, and what we're going to do is we're going to add heat to this. We're going to put a flame on it. And then we want to see what will happen. In other words, what its properties are and will it give off oxygen? Okay, now when we're in lab, those of you who are not hybrid, we will actually do this experiment. If you are hybrid and you want to know what the results are, then you have to go to the lab videos of Professor Gorbenko. Okay, I'm not going to tell you the answers here. Lab videos of Professor Gorbenko. Okay, he goes into detail. I'm just trying to summarize for you. Okay, so he will show you the results. So if I ask on an exam, which of these reactions give off oxygen, you'd better know, okay? And the only way to know is by watching that video or being in person. Okay, the next thing we look at is silicon dioxide. And you might remember that silicon dioxide, SiO2, is really just sand. Okay, and again, we're going to add heat. And we want to see if there's oxygen. Okay, we're also going to look at properties. We want to write down if it liquefies, if it changes color, if it gives off a gas, whatever it does, we want to see. Okay, now the test for oxygen. Don't mix this up now. The test for oxygen, right? If you have a test tube, there's my test tube. Okay, and that's my flame. If oxygen is given off, what you do is you put in a glowing, not a burning, a glowing splint, piece of wood. So you put a piece of wood on fire, right? It's burning. Then you blow it out, and then it's glowing. If we put it in the test tube, if it reignites, then yes, there was oxygen. Okay, so that's the test for oxygen. The test, I'll put it down here, the test for hydrogen is a burning splint. So you light a splint, a piece of wood, on fire, and you put it on fire inside the test tube, right? So there's my heat. There's our heat. And then we put this burning splint. We're going to put that thing inside our test tube, okay? And if there's hydrogen, then we hear what's called a hydrogen pop. Hydrogen. You get a little pop sound, right? Something like this. Let's see. Can everybody hear that? So you get a pop sound. So you put a burning splint for hydrogen and a glowing splint. Don't put a burning splint in oxygen. You'll have an explosion. Okay, so in these reactions, what we're doing is we're heating some of these silicon dioxide or sodium nitrate in a test tube. We're putting heat, a flame to it on a Bunsen burner, and then we want to see if oxygen is being released. We put a glowing splint into the test tube to see if the excuse me, splint reignites. Okay. The next thing we look at is what's called lead. Lead 4. Oopsie. Okay, my pen. Lead. Oh, come on, pen. Lead. No, it's not working. 1 second. Okay, lead 4. That's a 4, Roman numeral 4. Okay, oxide. We'll learn why it's lead 4 later when we do more chemistry, okay? And what this is Pb is lead, pyumbum, O2. Same thing, we're going to add heat, put that in a test tube and put it on a Bunsen burner, add heat, and do our glowing splint and see if we get oxygen, and also record if it liquefies or changes color, if it's clear, white, whatever happens, okay? The next thing we look at magnesium oxide. Okay, MgO. Again, we're going to add heat, put the glowing splint in, and see, till we get O2. O2 gas, okay? And then finally, we have potassium chlorate. Potassium chlorate. Okay, and that's KClO3. There's the potassium. Chlorate is ClO3. We're going to add that heat again, and we want to see what happens. Okay, do we get oxygen and what happens? So not only do we want to see if oxygen comes out, but we also want to see if there's any phase change, if it melts, if it's clear, if it's whatever happens, okay? Now, for us, what we want to do is we want to collect the oxygen from the air. Collect, well, not from the air, collect oxygen, okay? The question is, how do we do this? We're going to use a method known as downward displacement of water. Okay, I'll try to explain this in pictures, okay? First, what we want to do is we want to use a catalyst. Okay, now most of you, and I think falsely many people, a catalyst changes the rate of a reaction. So this is semantics, rate of a reaction. It could slow it down or it could speed it up of a reaction, right? And then it's untouched itself, right? In the body, catalysts are called enzymes. But I know you know that, right? You could say something that slows things down it's called an inhibitor, but it's also called a negative catalyst. So it's still a catalyst, but it just negative catalyst. So you see a catalyst can be positive or negative. It just changes the rate. It can speed up a reaction or slow down a reaction without being affected. Okay, and what we're going to do is we're going to look at hydrogen peroxide. Now, most of you, well, women certainly may know this, peroxide, or anyone who colors their hair, right? It's something that's used to color your hair. And here's the formula, H2O2. Now, in parentheses, I'm going to write it wants to be water, wants to be water, H2O, right? And eventually, if you have a bottle of hydrogen peroxide, it will become water if you leave it there long enough, right? And what happens is they usually put hydrogen peroxide in a brown bottle, right? Brown bottle. Why? So you get no light comes in, because light, remember, is energy, and light will come in and break this mother up, right? Break it up into water. So eventually it's going to turn into water, but that's going to take months, or it could take a year or 2 years or 3 years. Okay, so what we want to do is we want to speed this up. Okay? And what we're going to use is a catalyst. Catalyst. And the catalyst we're going to use is MnO2. And this is called, not magnesium, manganese dioxide. Okay, manganese, not magnesium, MnO2. Okay, and that's going to speed up the reaction. So what we're going to do is we're going to take our balanced equation. We're going to take 2H2O2. Okay, and now we're going to add our catalyst, our MnO2. And what we're going to end up with is some water. And that's a liquid, that's L. Plus, we're going to get our oxygen, O2, and that's a gas, G. And usually we put an arrow there to say the gas escape. Okay, so this is our fundamental reaction that we're going to break down the hydrogen peroxide into water and oxygen. Okie doke. All right, so here's the procedure, and I'm sorry for my poor artwork, okay? Okay, we're going to fill 3 jars with water. Fill 3 jars with water. So this is supposed to be 1 jar. This is 1 jar, okay? Make believe that's a jar. And then we're going to put a lid on it. Usually it's a piece of glass lid. Okay, so I'm going to put a glass lid over it, okay? And we're going to hold that, and then we're going to turn the bottle, or the jar, jar, upside down. That's why we have the lid on, so the water won't come out, upside down. Okay, and we're going to take that and we're going to place it in a trough. It's called a trough. Trough is a thing horses drink out of a trough, so it looks like something like that. Okay, so I'm going to draw the trough. Looks like something like this. Okay, I'll make a little boat thing. It doesn't matter. It's not that very straight. Okay, so there it is, and there's water in here. We're going to fill up the trough, right? So place it in a trough that we fill with water. Okay, and in the trough, you'll see something here, okay, with a little hole, and it's going to be a hose. It's supposed to be a hose. Okay, and I'll draw what that's going to in a second. So we're going to take this jar, and we're going to put it upside down. Right, and then we remove the lid. The lid. Okay. Now, what is this tube connected to? It's a tube that's going to go to the bottom. Right? It goes to the bottom and it feeds into the bar. So this tube, right, goes down here, and there's a hole that this goes through, and then we place the bottle over this hole. Okay. Now in this tube, right? This is going to come to a jar. And on the bottom is our manganese dioxide, MnO2. Okay. And in that, we're going to put our hydrogen peroxide, H2O2. Put H2, pour H2O2, hydrogen peroxide inside there. And then we put the lid back on. We put this cover back on after we pour the hydrogen peroxide. And what's going to happen is O2 gas is going to be produced. Okay, so O2 gas is going to produce inside that jar because we mix hydrogen peroxide with this catalyst. And that oxygen, O2 gas, is going to go through the tube. And eventually, and I'm going to redraw this bottle, this upside down bottle that was filled with water, right? And I'm just going to do something here. And there's this hole here that's connected to the O2, right? So in here is the O2 gas, and it's going to go in the jar. And as it goes in the jar, as O2 gas fills up the jar, the water is pushed out. So now what we've done is we've trapped O2 gas in the jar. Okay, so I'm going to redraw this. Okay, so now we have on the bottom, supposed to be our jar. Okay, now in this jar is the O2 gas. O2 gas, right? And it's a little bit of water. We want some water, a little bit of water. Okay. And then what we want to do, remember, this is all underwater in the trough, right? This is all underwater in the trough. Okay. And then what we want to do is we're going to take, okay, we're over here, and we're going to take our hand, this is our hand, and we're going to take the cap, it's the cap to the jar, and we're going to screw the cap onto the jar, back on the jar, on the jar, onto the jar. Okay, and then we turn it back up, then we take it out, take out of water, take it out of the trough. And we do this 3 times. And so what we end up with 3 jars of air, 3 jars of O2, each with a little bit of water in it, each with a little bit of water in them. Okay, so here's my jar, right? Whatever is my jar. There's a little bit of water, We can't see it, but there's O2 gas in there. Okay, and here we screwed on the top. Okay, so we have 3 jars like this. We each have 3 jars. And now we're ready to test our hypothesis. Okay. Okay, so now we want to test the hypothesis. Test the hypothesis. Now, what is the hypothesis? Well, this is the hypotheses. Okay, there's 2 of them. The first is that oxides of metals, I'll underline metals, because we're going to put metals in there, dissolved in water. So that's why we have some water in there. And that's why there's oxygen. And we're going to put some metals in there, dissolved in water, produce what's called a bases. Okay. And the other hypothesis, this is one. Our other hypothesis is this, that oxides of nonmetals dissolved in water produce, you probably guessed, acids. Okay, so that's our experiment. We're going to play with that. Now, the final thing is, how do we know if we have an acid or a base? And again, in class, we'll talk about what an acid is and what a base is. How do we know? How do we know whether we have an acid or a base? Okay, and what we're going to do is we're going to use indicators, what's called indicators. And there's two indicators we're going to use, okay? So let me tell you the first. The first indicator is called universal. You'll see why it's called universal. Universal indicator solution. Indicator solution. And if you're in the lab, you'll see jars that have UIS, universal indicator solution. And what happens is, if we take this with a dropper, if we add a few drops, to our solution, this universal indicator changes colors. Changes color. Okay, what color? Well, remember we have the color of the rainbow, Roy G. Biv. Well, if it turns red, orange, or yellow, it's an acid. If it turns green, then it's neutral. And if it turns blue, indigo, or violet, it's a base. So red would be the strongest acid, yellow would be the weakest acid. Violet would be the strongest base, blue would be the weakest base. Okay, that's why it's called universal indicator solution, because it tells you everything. Okay. All right, the second indicator, okay, is called phenolphthalein solution. Okay, so this is a tough one to spell. Phenol, PHTHALEIN solution. It is not universal. Okay, phenolphthalein solution. Again, this is another indicator that will change colors. Indicator that changes colors. Changes color. Okay. Now, phenolphthalein, what happens? I'm not going to rewrite that word. Okay, it turns pink, like a Barbie, right? Turns pink if the solution is basic, if the solution is a base. Now, I want you to pay attention. If it doesn't turn pink, then you cannot say it's an acid, right? If there's no change in the color, all you can say with phenolphthalein, if there's no changes, that it's not a base. And here's what you say, well, doesn't that mean it's an acid? No, no, it doesn't mean it's an acid. It could be an acid, or remember, could be neutral. You don't know which it could be neutral. Okay. All we know with phenolphthalein is if it doesn't change color, it's not a base. Could be an acid or neutral, but it's not a base. If it does change color, if it changes pink, then we definitely know that it's a base. Okay, so we're going to use the downward displacement of water, collect oxygen in a jar, and then we're going to mix in metals and non-metals and use our indicators to see if this really holds, if we get it acids or bases, whether you have a metallic oxide mixed in water or a non-metallic oxide mixed in water. Okay, more details, again, you can go to the lab videos on YouTube with Professor Gorbenko. Okie doke, that's it for this show. Enjoy. Hope it helps. Bye.